So I promised to give a very general talk on assessing unknown parameters of instrument finds by writing software. Seeing that this is 15 minutes, I will restrict myself to talking about wind instruments of the Olos type. And I suppose many of you, my dear friends, know why I'm doing this. I have now started working also on lutes, doing similar things, but I'm much more comfortable with this kind of approach, which I have been following since, I think, 1997. So I'm taking you through a quick tour of 6 chapters, as 6 chapters were in the template we were provided. So the problem is, for me, predicting the intended scales of wind instruments. So I'm mainly interested in the tonal material that an instrument was meant to provide to the player, to the audience. What is the problem with just reproducing it and playing it? First, the reeds are almost invariably missing. We have very few reeds, but those are normally not from Greek instruments, or if they were, they're lost. So we don't know the parameters, the extension of the reeds, how long was it, how thick was it. And sometimes even the inserts were broken, so a part of the instrument, or even a substantial part of the instrument, whole parts may be missing. So we need to assess how long these might have been, build hypotheses, which are consistent with, with what we know about ancient music, with what other instruments may tell us. Then there's the problem of varying tone hole sizes, which make calculation a bit more complicated than what we normally do with pen and paper. So we need formulas that we get from electronics, which give us quite accurate results, but with a complex evaluation procedure that can only be done by computers. Varying fingering, which holes are open, which are closed, that's not always such bigger problems, because all those holes are so large that cross fingering doesn't play a large role, but sometimes it does. So we need to assess that problem as well. And the worst thing, varying bore diameters. That also can be approached, given that the ancient bores are even extant, because many things are fragmentary. If the inside of an instrument was made of wood, we may have lost it. So we may even have to interpolate parts of the bore and experiment with different solutions here as well. So it gets all very, very complex. And then there's the bias that is introduced by the modern player. So if I make a replica, play it, I'm involuntarily and unconsciously driven to modify the intervals, the notes, to what I'm used to hear in modern music. I will adjust the semitones, the tones to what and that's so easy. It's so easily made, adjusting tones. But instruments were, I will try to show that, built to play as much unadjustedly as possible. So the instrument may have had a different idea of how music may have sounded, and so I may just not play what the instrument might play much more easily. What to do? Selecting approaches. Software for physical modeling. There is some software available, of course, which has limitations as to the specific target one wants to employ it for. So available and tested means you may just start to use it after having learned how to use it, but you can't easily extend it. And there's always some modern bias embedded in the results you get out of it. You would get normally either frequencies, and our brain is not well equipped for dealing with frequencies, which need logarithmic processing. So it may tell us modern notes and approaches to modern notes, and this gives us the modern grid of semitones, which is problematic. So the alternative is write software ourselves, if we can, and it's not so difficult to learn, and then we could just get what we really need. We will also only really learn what we need during that process. So that software, of course, does not exist, because we're just attempting to make it. So this will need some time. Time of whom? you might think about hiring a software engineer. That's a good idea. They can do things better than us. So we might expect it will save a lot of time, but it doesn't do necessarily, because we have to explain, and explaining and getting into loops of explaining and meeting again and again also may be a waste of time. On the other hand, writing software is time intensive. It's got a steep learning curve, but then we can get precisely tailored software. And what I think is most important, we can extend our software while we are learning, because we don't know everything we are going to need at the outset. We will grow, our questions will grow, will morph in the process of our research, and our software needs to keep up with that. If we are limited by the software, our research is unnecessarily limited. So I greatly encourage going down that rabbit hole of writing our software, extending existing software. So that's the path I will be talking about. And we will want to have some databases for our measurements, our information, our images, our literature, whatever. Again, there's two basic solutions. Local database, that's what I started with back in when online databases were not really available. That works everywhere. Take your computer with you, you have your database, you can work on it, you can enter it, but you need to work on your own necessarily. You're not connected to your colleagues working on the same database in different places. On the other hand, an online database enables collaboration, but it needs internet. And that may be a problem if you're sitting in the basement of a museum where there's perhaps no access to internet, or in some remote country where your access to internet is quite expensive. So I've used both approaches, and I think the optimal solution is to have both and to have the databases talk to each other, exchange the data they need. So that would be an example of my software datasheet, probably too rigid datasheet, but that's the old approach, more than 20 years, where we enter all our technical information needed for physical modeling of the pitches. And on the other hand, there's a much more modern image-based flexible database running on the internet, where we all can, especially now in the pandemic, can work wherever we are, at home, for instance, and then this would give the data to the old style database, while the old style database might export some data to be represented in the other ones, so we can achieve the best of both worlds in some way. Much more importantly, at which level do we want to model the behavior of our instrument? One approach is modeling the sound. So that's a big idea. But like all modeling, our modeling depends on the precision of our data. And where we don't have any data, the best modeling won't give us any reliable results because they're based on nothing. So in example of our wind instruments, it's mostly the double reed, which we don't have. And double reeds may have different geometries, different thicknesses, and different openings of the blade. That varies the sound just enormously. So I never tried to model the actual timbre of an instrument. Yeah. Another thing that I think that's not even remotely explored. Double reed, double pipe instrument is not just a mixture of two pipes that two different people might play at the same time. I believe, but it needs further study, that the interaction between the two oscillatory regimes built up of the air columns and the reeds, which are connected to the same pair of lips and the same mouth and nasal cavity and chest cavity of one player, would have a quite different behavior. and give a much richer and more variegated sound. So what I'm doing is not about sound, it's just modestly about pitches, which makes up for very fast calculations. So if I make a change in the parameter in my software, I can see the effects of the change immediately on screen. So experiment virtually fast. Again, my approach is the right one, right hand. So what's the workflow that I found most useful? That we have explored that, the variations of that in a few projects now. So we start with measurements, which might have taken in a museum, might have taken from older publications, which always need verifications. Everybody makes mistakes in taking measurement. It's just unavoidable. Mostly mistakes in the scope of 1 centimeter or half a centimeter, because we just mistake the larger marks on our rulers. And yeah, other kinds of mistakes creep in by copying from handwritten sources to printed sources. So yeah, no insult to point out that somebody has made an error in the publication. It happens to everybody of us. And I think we need to use the computer in loops of verification in order to sort our data out to make our data more healthy. And we have photographs, which can be very useful. I've once published a paper on how to make reliable and measurable photographs without all the very expensive and data-intensive modern equipment of 3D measurement. Just a simple camera would do in that case. And then feeding those results into the online database. For instance, using the program desktop frontend, so it can be done quickly and efficiently. And then this would go to the local database where I have all my calculations appended, also with a desktop frontend. And from here, we can go on. So from here, we can make schematic drawings automatically of the data, and then compare these back, for instance, to the photograph. Take the computer, overlay the photographs with the measurements, and it will immediately stand out if there's any gross error. And gross means perhaps more than a millimeter or so. That should stand out immediately. More difficult, of course, with internal measurements, what might compare it, for instance, with XRs. So another way of exporting would be 3D data, of course. So my program directly writes OpenSCAD code, which can then be converted to STL code and can be fed into the printer, but we don't need to feed it into print. We can view it on screen, and again on screen compared to whatever material we have, photographs or even the items themselves, to see whether anything went wrong here. So there's some data verification going on at that early stage. So if we have data from photogrammetries, CDs, 3D scans, whatever, that can also come in at this or an earlier stage. For instance, that would be an example where we've put one piece of a rather complicated geometry onto another piece that was created directly as an ideal tube from the data, so that, again, the useful approaches from two very different worlds could work together seamlessly and make an experimentable instrument. From here, we come to directly printing instruments, and so that's the Posidonia Aulus, which we have already seen in Angela's initial presentation, and that can then be equipped with reads, where we get the parameters of the reads, so that come from the predictions from calculations attached to the database originally. So make reads that are in agreement with this prediction, and then try it out, and that's the test of everything. Would they play the predicted scale or not? And so in the last 24 years or so, I found that this kind of approach seems to predict pitches very, very nicely. So it's possible to play the pitches from the computer, the predicted played instruments. Once you set up the highest pitch, say the highest pitch, which is most unstable, then you should reach the other predicted pitches just by closing one finger hole after another. Yeah, then one might go on to produce the real thing. Here we have fabulous Peter Holmes of Middlesex University presenting a copy of one Pompei-Aulos pair, and those then should work as expected. Big advantage is that a very large part of this whole process only runs within the computer, so there are no possible copying errors between different bits and pieces. Nothing is programmed anew introducing data, but here everything goes down a well-defined path. As long as the software works nicely, the results should be correct. And there's the validation process, the connecting the whole thing back to the measurements so one can detect them. So printing is not everything. Here's an example of CDC lace. So as you can see, there's a model of a part of an Aulos insert, and this is then produced inside this chamber by lacing it automatically, and should also produce a very exact result. What are the advantages? So first, we can make tailored extensions. For instance, this window here, where I can draw around pieces of Aulos which are unknown how they belong together, and experiment with different configurations and see immediately the musical results attached to that. And the integration of information we need to assess the results. Ancient pitches, you can see here, in addition to frequencies and cents, we also have ancient notes here, which show immediately what that would mean in connection to the fragments of ancient music. Or automatic scale matching, so a number of scales that are described by ancient theorists, and we could see how a scale predicted for an instrument would fit in with that. You can see that this one fits in very, very nicely with only a few cents of deviation. Then automatic search for optima. So this would be a map of different reed extensions, and the lighter regions are the better harmonic regions, and this would be the optimum, which is here used in this particular setup. Yeah, does this proof harmonicity approach indeed work? I'm almost there. I could show that getting better measurements, achieving better data, we would also get a higher machine-defined harmonicity, so that this approach may even function as a measurement of data health, at least with certain instruments. We cannot know yet whether this can really be generalized. But we're working on it. We need more data, more alloy. So as a conclusion, for any new subfield, so I've done alloy, I'm starting with lutes. Other people are working on brass instrument. If you start anything new, yeah, write your own software. You can define what you need, where you want to compromise, and you can have the joy of playing Lego with computer code. For alloy, team up with somebody who already has software tailored for the purpose, and that's an invitation to team up for a future project involving the huge array of unstudied alloy fragments out there. Thank you, everybody.